Shall we start? Yes, can you hear us? Hello?
Not so well.
It's not working. Good afternoon, GeeCON. Fuck. One more time. Good afternoon.
Good afternoon.
Thank you. So before we start, I was thinking today in the morning that I should actually thank you for coming, because you know, you came to session with two grumpy old metalheads talking about performance, so they think nobody cares, mostly. And you could be sitting now in your at home, watching another domain-driven design training conducted by people who didn't touch code in since internet inception, and you choose us. So I really appreciate.
Or create another model.
Yeah, or create another model that doesn't work, and then you need to fix it. Because what I usually say about domain-driven design models is they are all correct until proven otherwise by performance tests. So, so welcome. I'm Jarek. Where's my clicker? I'm Jarek, and works? Yeah, should work. You can send us comments about my introduction about domain-driven design trainings. I can respond to questions. I'm Jarek. I'm a staff engineer in Neo4j. I spent, wasted, whatever you call it, I have my painkillers here. Last 5 years as a performance engineer, I'm in benchmarking team in Neo4j. Neo4j is a graph database. Maybe someday we'll do the presentation about Neo, because we should talk about Neo. And yeah, I spent my 20 years with JVM doing weird stuff. And I remember that there was only one garbage collector, there was no JIT. And I don't know how it happened that this language was such a success, taking into account how the first version looked like. And here is my fellow.
So, my name is Michał. I don't know if it's a good description, but I had the honor working with Jarek in the team. And yes, I'm working in Neo4j also in benchmarking team as a software engineer for around 2 years. I'm working with JVM around 20 years. I remember the times when Spark platform was the only one using all of those features and that Sun created then. And yeah, and also I remember times when we didn't have any version control system, and we are just sending all of those binaries to the Spark or by floppy disks or something. Nowadays I'm a coder. I'm trying to code, create some tasks, analyze them. Problem solver as an engineer, I'm trying to resolve not only software engineering problems, but also some mechanical ones. And eternal grump. So yeah, what is going down?
Yeah, this is us in the morning.
This is us in the morning at work. So we've got something called regression sessions. And we are trying to find what's going on after performance tests. We're analyzing the results and trying to find what's going on there. And it looks like that. So it represents the situation that we found a regression, and we forward all of those things that we found to another team, and trying to hide to not find us and claim that it's our fault. Yeah. So we found that currently no one cares about performance.
Until your credit card is connected to your AWS account.
That's another story. Why? Because we are still living in a time that hardware is cheap, all of those resources we can buy, and we don't care about it. We don't care about optimizations and all that stuff. But it's going to change, because all of those costs related to the cloud services are getting higher and higher. So nowadays, I think that things related to performance and monitoring all of those things are changing a little bit. So welcome to our world. where everybody lies. So we found that a lot of products, a lot of benchmarks, a lot of performance articles are saying that the product is the best, that everything should force you to use it. But those things are lies. You should just test it and check how it will work in your environment.
Okay, so the structure of this talk, we will be discussing like 8 performance testing anti-patterns. So if you are like new to performance testing, it will be like good introduction session. If you are long enough in performance testing, Nitsa, you will be like, yeah, you're right. You'll be just doing a lot of nodding. Nothing new here, except jokes. So, you know, this is carefully selected 8 performance testing anti-patterns. The first anti-pattern, I think from my opinion, the most important, that's why it's first, is something I call numbers game. So when you think about performance testing, you usually think that it's all about numbers, you know, latency, throughput, resource usage, you know, how much memory, how much network, operations per second. And we are so focused on these numbers, and whenever you think performance test, it's like, okay, the outcome is some magical number that will tell you something. It's a one of big misleading lie, because people make decisions based on these numbers. Somebody tells you that, you know, MongoDB is fast, and you make a decision to use MongoDB as your main database. Or somebody says Akka executes this number of requests, and based on some fancy blog post, you make a decision to use this as a central part of your architecture. And there are lots of weird and important decisions you make based on these numbers. Yeah? But something has, on average, 50 millisecond response time. And you choose, sometimes you choose technology based on the performance numbers. Sometimes you choose code optimization techniques based on performance numbers. But okay, I will do inlining, I will lay out my object differently because performance numbers are saying something. And then the long forgotten art of capacity planning, you know, the capacity planning is now your Visa card, but you make a decision how much stuff you need, resources, based on the performance numbers. And why these numbers are wrong and shouldn't be your ultimate goal when you do performance testing is because there are so many factors in your system that impact your system, but this single number doesn't tell you the whole story. Okay? So the question is there a value in performance testing? I think it's not about numbers, in my opinion, but performance tests are about understanding the structure and behavior of the system. You run performance tests to understand how your system behaves, what it's doing under pressure, and how it behaves, and how you can optimize it. It's not about these numbers. They are important to find regressions. This is what we do in our team. We use these numbers for regressions, but we don't use these numbers to make decisions how to structure your code, okay? And I think my favorite term that I learned when joined Neo4j is something called benchmarking. So basically, there are 2 kind of anti-patterns. One is benchmarking wars. When you see somebody publishing their database, you know, scales to like trillion of entities, and then the competition responds, yeah, we are even faster. And this is like endless series of blog posts saying that we are faster. And there is a special case of benchmarking wars called benchmarking. And benchmarking happens when you select one feature from a product and you base the whole performance of your product on the performance of a single feature. So yeah, in this specific case, we are faster. And that proves that the whole system is faster because it's faster in this specific case. Another problem is that probably most of you, like me, didn't go at the university to statistics classes. I prefer drinking beer over statistics, you know. And to understand performance tests and performance test results, you need to understand performance statistics a little bit. Because the problem is, in most cases, people come to you and say, on average, I got 200 milliseconds, okay? The thing is that average is one big lie. Normal distribution. What average means? If you have normal distribution, average means that 50% of your customers or of your requests will get responses under this value. The remaining 50 will get longer responses time. So it means you will have half of your customers happy and half of your customers are happy. So every time you see blog posts saying, oh, on average, we do this, we have this latency, just throw it into trash can. It's useless completely. There is another thing which is kind of interesting is you think that for the same request, the system will always respond with the same, in the same time. Yeah, I ask for this user ID 1000, and I will always get the same response latency. The truth is that there is something called random variable that can cause that your response time will go from almost 0 to infinity. So this is average of this different tries to execute request. And of course, links to articles, because this is not the session about statistics, but if you start with performance test, at least do some basic introduction to statistics, because it will help you to understand. The solution to this problem is always talk about percentiles and say, okay, on 99 percentile, this is our latency numbers. And of course, try to share the whole histograms, because they tell better story about your system performance. And one last thing from me is I love this notice from the JMH. When you run JMH, the Java Microbenchmark Harness, every time I see it, I think this is one of the best quotes. These are just performance numbers. To gain insights, run profilers. So what's your opinion on profilers, Michał?
On profilers. So it's anti-pattern number 2, profilers. Profilers also are lying. Why? I don't want to get into the details of how profilers working under the hood. So
especially
I would like
you have Nissan here. So.
Yeah, true. So I would like to ask you to see the presentation of Vakat and read some articles about the profilers, what's going on under the hood, and why they are lying, and why we should use it with some depths in the end.
Grain of salt.
But I would like to summarize it, the whole things that are introduced there. So we can divide profilers into 2 different solutions. So one is working as a sampling profiler, and the second one is working on instrumenting profiler. Sampling profiler, we can treat it as a discrete system. So on each sample, profiler trying to get all of stack traces, threads, statistics, and some other things for analysis. But there is a risk that, for example, some short part of the code can be executed between those samples, and profiler will not catch them. So we'll lose maybe some strategical information there. And there is another thing, so instrumenting profilers. Instrumenting profilers working that way, that tries to inject and modify the code to get all of those things from there, but it changes the code. So on the production environment, code will work different way than on the system where you are going to measure the performance. Great examples for instrumenting profilers are managed runtimes, for example, for .NET or for Java, where we've got under the hood all of those things like garbage collectors, safe pointing, just-in-time compilation and and also some other optimization techniques. And if we will inject and modify the code to get some additional information from there, it will cost some of those things. But you have to remember that, for example, instrumenting profiler is a great tool to use when you would like to get all of those details and execution steps that are going on under the hood. It will cost a lot, but it will describe all of those things under the hood. But there are some solutions about it to resolve things that profile is introducing. We have to get some basic knowledge about which profiler we should use and why, and how it works under the hood. We should also try to not use only one profiler in that case. We can understand it as a doctor. So for example, if you've got broken arm, you can use X-rays to get some knowledge about what's going on with your bones. But you can also use additional tools like ultrasonic things to get some more details about what's going on with other things of your body around the broken bones. And in the end, you will summarize all of those things and get some more details. So the best solution is to use few different profilers and merge all of those results and analyze it. What else? During the profiling, before you start, it's great to create some baseline for them. So the point where you can say that it's 0.0 without any load, without any actions under the hood. So
like running on empty database,
for example. Yeah. So this will be the baseline that you will try to find all of those results, the difference between load and what's going on there. Also, you have to watch out with the environment that you are working on with those profilers. Each operating system works differently, managing things related to memory and I/O, so you have to also take it into the account. And also, yeah, numbers in the end are not telling the whole truth about the results of the performance.
Number 3, okay. So the next pattern, anti-pattern, is we are often asking the wrong question because we are running the performance test and we are saying, okay, this is the latency or throughput or something. But sometimes it's not the right question because the performance tests have layers. There are different things, different ways and different types of performance tests. And first you need to ask yourself what you want to get from the performance test. What is the end goal? And it could be latency test. You measure latency and you want to know end-to-end transaction time. Sometimes you measure throughput. Okay, what is this throughput for the least number of concurrent users? Sometimes you know that Black Friday is coming. You are expecting 10,000 users, concurrent users, and you want to know if you will handle such a load. So as you see, there are different questions you ask. And sometimes it means you need to design this performance test differently. Of course, my favorite kind of test is stress test. You hit so hard until the system dies. And answers the question, what is your scalability, what is your scale limits? Of course, you have endurance tests when it's like similar to stress, but you run it for extended time, like, sometimes hours. I don't know how hours so long run, it's like 2 days, something. So then you are trying to catch like nasty, small, tiny, memory leaks, resource leaks, and deadlocks, but won't happen within like 15, 20-minute performance test run, and you need extended period of time to understand if something is hiding, like especially nasty performance leaks. And then capacity planning, so how much resources you need and how much resources you will need in the future if you start to scale. So we are going from 10 users to 100 of users, how much CPU network or throughput, I/O throughput you will need. And of course, degradation test, I never in my career did it, but basically you run the performance test and in the meantime you break one of the components, like you shut down database or shut down connection to Kafka. Of course, secret breaker comes in, and you want to see the performance of your test and behavior of the test. Remember, performance tests are about the system behavior. So if you run performance tests and you degrade part of the system, it will tell you how the system will behave. when something is broken, especially in microservices world context. So you need to pick one. And when you design and decide to run performance tests, you say, okay, what's my question? Is it latency, throughput, load? And there's a special category that's like deep in my heart, microbenchmarks. But I think it's super hard. And sometimes I regret I went this path because it proves constantly that I know shit about systems every time I write microbenchmark. But they are pretty good at finding, like catching the point where the system is really slow, where is the bottleneck. They're really good to like fine-grain this specific method where we have a problem. Because I think about microbenchmark like a unit test. So you have isolated, you don't run the whole system, you don't start all the databases, you don't run waste AWS resources, you just exercise single function of the system. By function, I don't mean method, but some kind of specific behavior. So it's isolated from other components, you will not have noise from background jobs and something and others, and it's really good. The infrastructure is much easier because it can run on your laptop. And I think they are still hard to get. But it's an interesting journey.
Endurance tests. I remember, for example, that we've got some endurance tests when you forgot to remove EC2 instances.
Yeah. No, I didn't.
Okay, so another anti-pattern. Latency is not throughput. We found that currently a lot of people are trading latency and throughput as the same term. They're equal for a lot of people right now. But it's not true. Latency is a function that will tell you how latency is changing during the utilization of your system. And throughput is a value that will say you how many data can you transfer, put, or process during a defined period of time. Here's a great example, just a chart that will, and that is going to tell you how utilization is have the impact on your latency. So response time is changing during the utilization function. And why we should take care on those things? Because latency, well, maybe different way. We, as an engineers, during the performance test, should find the point where latency is not changing dramatically. So we've got requirements that latency for our system should be, I'm not sure, 10 milliseconds. And we should find the point where throughput will break that case. It will tell us exactly how our system is performed. Another solution is to create some defined throughput requirements, for example, 1 million requests per second, and try to find what is the latency for that, and try to optimize all of those things to get latency lower.
It's like don't do what our competition did some time ago. They publish the latency numbers, but they didn't tell you how many concurrent users they have. This is the kind of marketing around benchmarking. So every time you see article published without saying something about latency, not telling you about the throughput and number of concurrent users, just throw it. It's just a pile of bullshit.
Mm-hmm. The same situation with average.
Yeah, like the same situation with average. Oh, the thing is, with performance tests, that you want to run it in isolated environment and get some impression how your system will behave when you deploy it to production. And this is like getting it real, because you don't have all of the money in the world to replicate your production and have exactly the same performance test environment as the production, so you need to scale it down. And there are like a couple important things you need to take into account, including that modeling workloads for performance tests can damage my brain and your brain. So what you need to take into consideration when you design performance tests? This makes me like angry. Think about actors in your system, because not all people in your system behave the same way. If you take, for example, e-commerce site, some people, mostly like 80% of people, are just doing simple search, navigating web pages and looking for products to buy. Then you have like 5% of people who are actually adding stuff to shopping cart, and then you have 1% spending the money and doing transactions with credit cards. So if you design system performance tests, first get to the production data and say, okay, on average, we have like 80% of people doing search, and the remaining people are adding stuff to their cart. And shopping cart, and try to design the system in this way. Sometimes you have like actors that are doing some kind of background jobs. It not necessarily have to be the users. Actors can be other systems that use your system. So it's important. Another thing is datasets. So what kind of data, how many products I have in a database, how many users I have, synthetic users I have in my test database. Another thing that you see where the madness is going, you just want to design simple performance tests, and this is the things you need to consider. It's like traffic shaping. Some systems have constant, 1,000 requests per second on 8 hours a day, or 24 hours a day, 7 days a week. Some systems have like regular spikes. Every hour they have spikes in usage. So your performance tests will need to shape the traffic in this way, because the system can change behavior. Like with Java, when it's quiet, the things can get decompiled, and when you get the traffic, the JIT will fire again and will start to compile things. So you will have to wait until you reach the maximum performance. So you need to emulate this behavior. Traffic types of operations. This is something that you should. It's kind of connected to actors. You have delete, remove operations. You add stuff to shopping carts, remove. So you need to have all the kind of operations into your performance script, testing script. Operation dependency. Usually, this is like something we can call customer journey. So basically, somebody enters, does the search, and adds stuff to shopping cart, and then checks out. So you need to first understand your customer journey, because then you will know what kind of operations, what is the order, is it insert before update, or maybe then this delete and then select. So you need to understand your user journey in the system. And then operations interleaving, so things can happen concurrently. Somebody is checking out something from your shopping cart. At the same time, backend jobs add new stuff to your warehouse. Interesting contention. So you need to really watch out for all these kind of things. Time, how long you will test it. Data retention, because the system database during the test will grow, and your production database will grow as well. So you need to take into account that some data are permanent, some data in your system will get deleted when the transaction is finished, and so on. So there is like a lot of factors when you design performance tests. The thing is, question, is there somebody here that has a system without a database? Like no database. What happened?
Just translating data between...
Okay, lucky you. So basically, after 20 years in this business, I think at the end, it's always database problem. Somewhere at the end, there is a database. And you need to, when you design your performance data sets and performance scripts, you need to take into account the cardinality. Do I have indexes? I was sometimes running performance tests ages ago on the system that didn't have indexes the same as it was on production, because nobody knew what is the current set of indexes on the database. And of course, the data life set. So you need to take into account. Because this is, at the end, it's a database problem, probably, mostly. Yeah. So what's the problem? The problem is the cardinality. Imagine that you have a request that will return like your shopping cart, and your shopping cart will have different number of items. Sometimes 1, sometimes 100, sometimes 200. So the response to this query will be different, okay? So if you have different cardinality, you can expect different response times because, for example, databases will make different planning decisions and the plan for this query can be different. That's the one thing. The other thing is the live data set. It's like funny because people say, oh, I have 10 terabyte data set, or I have 20 terabyte data set. And I say, I'm not impressed. What is your live data set? What is your hot data? Because you can have like 90% of the database cold, nobody thinks uses ever. So try to understand how much of your data is actually used and how much memory you need to fit it in, how much memory you need to fit the data in it, okay? Because I think this is what I learned in Neo. Like my biggest enemy, I think, is the result variance. So this is the case when you look at the performance test, you run it in the morning, it's 10 millisecond response time, you run the same code base, same commit SHA, and you have 20 milliseconds. And when you run it on the other day, it's 100 milliseconds. This is like throwaway performance test. It's bad design of queries, bad design of parameters, bad design of data set, because you have result variance, which comes usually from the low quality of the data. And the problem with result variance is that it's a noise and it hides outliers. Because sometimes it can hide that you have real problem. Because if you cannot trust your response times and your performance data, you will say, oh, this is just variance. And maybe this is not variance, maybe this is regression. Yeah? How to deal with it? It's really important to, when you run performance tests, monitor your system. And I saw it so many times that people were coming to me and saying, okay, this is my JMeter performance results, numbers, this is the chart. And my next question is, where is your observability charts? Where are your response times, the database behavior, your other components? So look at the other metrics. On the other side, if you run performance tests, it's really good to monitor how many records, entities you return from your responses. Because when your performance test sometimes returns, like query returns 1 record, and sometimes 100, this is where the variance comes in. And for example, we have, how it's called, Mateusz? We call it heat map, yeah. So what we do during running, so actually Mateusz wrote it. So we are counting how many records we return per every query, and we'll show it in a nice form of the result heat map. So we know what is the distribution of the sizes. And one thing we experimented some time ago, and kind of now don't look at it, it's coefficient of variation. So basically this is like one statistical measure that will tell you the quality of your benchmark, because it will normalize the standard deviation. And last thing, I have just one slide, modeling your testing environment. What is the instance size? Do I have 16 core on production, or I have 32 cores on production? Network isolation, don't run tests on production. I did it. Infrastructure isolation, don't run performance tests on the database that it's shared with production. I did it. So you need to be really careful when you design your performance environment, test environment, and performance scripts. And remember, it will always get worse in production.
Okay, anti-pattern number 6. All of those things related to measuring performance cannot happen without any load that you can generate. So it's related to load generators. Currently on the market, we've got some solutions, for example, JMeter or Gatling.
K6S, yeah.
Yeah, each technology has so. So you've got a lot of options to do, to work with it. Yeah, but it creates also some issues. The great example that describes it, it's a term created by Guild team. Coordinated omission. So coordinated omission is a description for the situation that system under the test creates some impact on behavior and how the load system is working. Great example of it is created by Ivan about coffee service and how it can behave and how it can be found on that simple service as it is described here. Yeah, load generators. We can split it to two different models that they can represent. So we've got open model systems. It's a model where each request for the load is created independently. So you can imagine it as we are creating new threads that are independently creating some new load. And there is also a closed model system, and it works that way that it waits for the previous system, previous request to be done, free those resources used for that, and try to another one. In the real world, we can simulate it with open systems. It's more representative for the real system to simulate it with open model. Why? Because you can create some random calls for independently on time and other things from the external system. Here is a simple example how closed work works. So we've got loop, and we are calling request and waiting for the response. If it will end, then we can call another one. In open models, we are using, for example, threads. So each thread will call request and response without waiting for an additional one. So it's more like real scenario when users are trying to call to your system. Here is an example, extended example of the system where we are calling request, waiting for response, calculating latency, and in the end, we're calculating also the throughput.
And this suffers from coordinated omission.
Yes. But it works in theory. Why? Because you can create a lot of threads. Right now, we've got also virtual threads. But it creates another problem with accessing resources. I/O resources, network resources, memory resources, contention, and other stuff. So in the end, we can find that it's not working as we expected. There are two solutions for that. We can introduce two different schedulers for those request factories. We've got static scheduler and dynamic scheduler. In static one, we are firing the request on defined timestamp in our timeline. In dynamic one, we are just firing without taking care of what's going on with previous one. But if we are going to do it that way, we should also manage somehow how all of those requests will be created. So we've got two solutions. We've got queuing approach, where we can just put all of those requests on the queue, create a thread pool, or in a closed word, just single thread and asking for, as a consumer, just taking one each by one. And in dynamic system, we are just creating a thread pool and taking all of those things from requests from the pool, from the queue, and trying to simulate the system. That's how it works. But yeah, we should take into account that, for example, we should also introduce some managers and other processes that will manage all of those things. And we've got also queueless approach. Queueless approach is working that way that we don't have a queue, but we've got thread pool. And we are going to ask for new requests on each amount of time, but we are not going to fire request if it's taking longer than our expectations. So for example, imagine the situation that you are going to launch request each 10 seconds, for example, and you are waiting for that. And after 10 seconds, you are trying to fire the request, but there is no free for execution thread. So we're just skipping it and waiting for another execution to find some free resources to use it. What solution for that? We can use it, for example, when our system is in high load and we are not going to crash it. If you are going to use load generators with all of those things from previous slides, so with models, queuing, and other stuff, you have to take into the account that there is something like latency correction. For example, you are going to launch system right now, but the system is busy, and you have to wait, for example, 5 seconds to launch the request for measuring the latency. So you have to take into the account the calculations that you waited 5 seconds for that, because it will, in the end, it can just false your results.
Basically, you don't have to worry about it. And until one condition, you start to write your own load generators. Because, most of the tools, JMeter, Gatling, have this problem already solved. But somehow, for some reason, you want to be brave enough to write your own load generator, you need to take into consideration all the, coordinated omission, latency correction, and these different approaches.
Yeah.
So don't worry until you have to.
Yeah. So still statistics and calculations. Yeah.
It's me. We are getting closer, and probably on time than usual.
Looks like that.
Okay, this will be short, but it's super interesting. Is measuring time takes time. Yeah, physics, Sorry. So, yeah, if you ask your operating system what is the time now, it will give you back the time, but it will be already in the past. So, one thing is it takes time. Second thing, you don't have like 1 nanosecond granularity. Something changed recently, but yeah, it's maybe it's getting better. And the other problem is scalability of latency. I mean scalability of the time. It means, if you ask too often your operating system about time, you can end up in bottleneck, performance bottleneck. And of course, it's time for Alexei slide. So I think it's pretty old, like 6-7 years old. But interesting observation that you cannot observe something that is faster than 30 nanoseconds. It all depends on your operating system, CPU architecture, and all this kind of stuff. But measuring time takes time. So it's not cheap. You don't get 1 nanosecond granularity, and you will have a scalability bottleneck because it's kind of contention on getting the counter timer value.
Yeah. And the last point from this presentation, anti-pattern number 8. You are looking in a wrong direction. So it can be called like a sum up of all of those things that we said just in those previous slides. You have to take care on all of those things that are getting and are working around you and during all of those tests. So it's not so easy just to take latency and throughput. You have to also check, for example, use tools like VMstat, IOstat, try to get what's going on with the system, with swapping, with memory management, with operating system. Maybe some additional traffic appeared in your system or something.
Or errors.
Or errors.
I have a funny story about errors.
4.4.
Yeah. So long time ago, many ages ago, I was doing performance management for one of the SaaS systems, and we did release, and my boss rushed into the room shouting, "We are 40% faster. It's unbelievable, best release this year." That was really fuzzy or so. And I said, okay, 40% faster? It doesn't happen in performance. You know, if you see something 40% faster, it should trigger like, oh, something is wrong. So we started to look at it, and what we found out, developers changed the address of the REST endpoint and didn't tell us about it. And our JMeter scripts were, you know, sending back 404 is pretty fast. So measure errors and look at errors not only at the application level, but also at the operating system level. Because maybe your performance, your benchmark is faster because you have errors. And most of the systems are pretty fast at returning errors.
Also analyzing it because,
Yeah.
for example, you have to be sure that you are testing what exactly you are testing.
Yeah.
And the final boss. So
It's on me.
stage is yours.
Okay, this will be really personal. We have feelings, you know, people doing performance have feelings. I think the biggest anti-pattern is not having performance tests. Why I think so? We can think about money. It's okay. You know, if you don't have, if your system is slow, you will pay more, and Amazon will get richer, and Jeff Bezos will get a bigger boat. It's okay if you like him. That's fine. But I think there's one thing that I'm kind of obsessed for the last 3 years is trees and climate change. How do you feel about it? You're running your system in Node.js, calculating Bitcoin or doing AI with Python. No, okay, maybe Python's a better example. But we are so. I think we will be guilty soon of CO2 emission. There is quite interesting research by Stanford University, or I don't remember exactly, it was Stanford University. That in 2036 or 7, 30% of the power, electricity will be used by data centers, and we will be using artificial intelligence to generate cat pictures. Humanity, you're lost. So I think it's also important, not only from the money perspective, from understanding the system, but I think also from the, think about my kids and yours as well. Thank you.
Especially that we are not using scalability as just increasing our hardware inside.
Thank you very much.
Thank you very much.
Questions? Do we have? Yes? Should we click the Slido? Yep. Oh.
Interesting.
You have questions on your? Okay. Będzie szybciej.
Tak?
Nie mam okularów.
Okay, first question. Not to trust single profiler or single type of profiler?
No, don't.
Don't. Try to use different profilers with the same scenario. So you can just use, for example, JFR, an async profiler, and what else?
There's really nice talk from Richard Starin about how async profiler takes samples in a different way compared to JFR. They are both sample profilers, but they are catching and in a different way, and they are doing the memory allocation profiler in a different way, and you need to understand how they do it. So I wouldn't trust single profiler. If I would trust single profiler, I would at the same time take a look at observability metrics, because sometimes you don't see things on profilers, but when your counters say, okay, the method was actually executed, but because you see, HTTP endpoints being triggered on Grafana, and you don't see these things in profiler. So at least it doesn't necessarily have two profilers, but at least two sources of truth. I mean, the information is like profiler and metrics.
Also, using profilers costs sometimes a lot, so you have to take also it into the account. Okay, next one question. What tools do you use for microbenchmarking?
In Java world, it's only one simple. This is like golden standard. It's JMH, Java Microbenchmark Harness, and I think it's really good because the same tool is used by the JVM developers to do stuff, so that's easy question,
Yeah.
JMH.
Debug profile on production. Anyone?
I think with it's this topic of continuous profiling, and you know the current profilers like async profilers are so good, but I wouldn't be worried to run your system all the time with the profiler on, because it's sometimes 2-3% of your time, of your request time, but in return you get data. But something crashes, you can travel back in time and say, okay, this is what happened. I think the great tool is, for example, Pyroscope from Grafana, which it measures, captures frames with async profiler, and then you can see what your system was doing like 2 hours ago during outage. So you can travel back in time and see exactly which part of the system were executed. And the 2-3% of overhead, it's worth it, I think.
Also, currently on the market, you've got a lot of APMs.
Yeah,
so
yeah,
you can monitor your production. And also, I think, profile it.
Yeah.
Okay, another question. Microbenchmarks amplify performance issues of a single component. But how do you choose which component to test if you cannot trust the profiler?
I think this is where the layers of benchmark performance test comes in. It's like in our case, we have like high-level benchmarks that run the whole database, and we run like the whole query. Okay. And then when we find that query is slower, we know which functions were executed when running this query, like operators, database operators, and then we can say, okay, the query got slower, and we have microbenchmarks which cover specific parts of this query, specific operators. So we can go from up, the whole system level, and then nail down with microbenchmarks.
Yeah, but it can create a whole structure of the things that you can have to maintain, because microbenchmarks are great to see the whole product in that case. So we're using it as a view for whole product profiling. And if we've got some tricky place and we are thinking that it should be somewhere there, we are just analyzing the micro profilers where, as Jarek mentioned, we can treat it as some unit tests with some part of the code and try to analyze it. And the last question, if it's always worse on production, maybe we could design some kind of pessimistic scenario so that we could guarantee performance no worse than X.
Oh, tricky. I don't have an answer.
Pessimistic scenario.
I think the stress tests are kind of pessimistic scenario, because the stress test will tell you cannot have more than 20,000 concurrent users. So this is the limit of your system. I think what can be helpful is do scalability, like with the capacity planning tests, where you say, okay, I run for 64 concurrent, 100 concurrent, 200 concurrent, see how the system scales, so then you will know where is the breaking point, probably by extrapolating. But it's like tricky. There are books on capacity planning. So.
Yeah, true. And that was the last question.
Thank you very much.
Thank you very much.